We saw in a previous video that spontaneity for the vaporization process occurs when the increase in entropy for the system has a greater magnitude than the decrease in entropy of the surroundings. So, spontaneity does not rely on a positive entropy change for the system. It relies on a positive entropy change for the universe, that is, for the system plus the surroundings. Let us revisit some of the spontaneous processes we discussed in the first lecture in this chapter. A gas spontaneously expands in an evacuated container. During this process, the system's entropy increases because molecules of gas occupy more space in the final state than in the initial state. This process occurs without exchange of mechanical or thermal energy with the surroundings, that is W equals 0 and Q equals 0, so Q surroundings is also equal to 0. For this spontaneous expansion, delta S is positive and delta S surroundings is equal to 0. Blocks of metal, initially at different temperatures but thermally isolated from the surroundings, will spontaneously evolve toward thermal equilibrium when placed in contact with each other. During such a process, there is a dispersal of energy in the system, that is, the entropy of the system increases. However, the system has adiabatic boundaries and cannot exchange heat with the surroundings. So Q and Q surroundings are equal to 0. The change in entropy for the system is positive, and that for the surroundings is equal to 0. Let us now consider the isothermal mixing of pure ideal gases. When gas molecules A start mixing with gas molecules B, the entropy of each gas increases because mixing is a disordering process. So the entropy of the system increases as a result of mixing. Furthermore, intermolecular interactions are negligible in ideal gases, so mixing does not give rise to the release or absorption of heat. Q is equal to 0 and Q surroundings is equal to 0. The change in entropy for the system is positive, while that for the surroundings is equal to 0. Consider the spontaneous reaction of molecular hydrogen gas with molecular oxygen gas to form water liquid. Gases have much larger entropy than liquids or solids, so for such a reaction, the entropy of the system decreases. Furthermore, this reaction is very exothermic, that is, Qp and delta H of reaction are large in magnitude and negative. Consequently, Q surroundings is large and positive. So delta S is negative and delta S surroundings is positive and very large in magnitude. Consider the spontaneous crystallization of water at 10 degrees Fahrenheit and 1 atmosphere. During such a process, the system orders and its entropy decreases. Crystallization is exothermic, so Q surroundings is positive. So while delta S is negative, delta S surroundings is positive and larger in magnitude than delta S, and crystallization is spontaneous at 10 degrees Fahrenheit. Finally, examine the reverse process called melting, which for ice at 70 degrees Fahrenheit and 1 atmosphere is spontaneous. During melting or fusion, the entropy of the system increases. Fusion or melting are endothermic processes, so Q surroundings is negative. For the fusion of ice at 70 degrees Fahrenheit and 1 atmosphere, the change in entropy of the system is large and positive, and that for the surroundings is negative.